Hello. Okay, see. 0.5. Now this slideshow chapter 5. Okay, everyone see me? Should be fine. Okay. So any question from this time? So this time we finish chapter 4, the continuous time Fourier transform, and we use it to solve constant coefficient linear differential equation with initial rest condition. We see that we can just do Fourier transform and you can just do a Fourier transform on the whole equation, and by the convolution property of Fourier transform, you can divide big Y with big X, then you get big H, so you know the system function. So you see that for a differential equation or any LTI system, in the frequency domain, you just have a simple relation big Y equal to big X times big H, so and everything is easy. But anyway, that was past week, and if we have no question, then we are going to the next chapter, chapter 5. Now it's discrete-time Fourier transform, and we have a small picture of a Fourier family here. So we are finishing up the list of our Fourier family. We have the Fourier series in chapter 3. Those are for the continuous time periodic function. Then, so Fourier series is for both discrete time and continuous time. So we have a continuous time Fourier series, and in this chapter 3, we also have a discrete time Fourier series. And it's something very nice because it always converge. And then in chapter 4, we just finished, it's the Fourier transform. So it's the Fourier transform for non-periodic function, and we found out that you have a Fourier transform, and in a non-periodic function, you do Fourier transform, it becomes basically another non-periodic function in the frequency domain. And it's very symmetric back and forth, it's very nice. And now we are going to talk about the discrete time Fourier transform. So it's still a non-periodic function, but it's discrete time. And we are going to see, because it's discrete time, and just like all the discrete time discussion we had before, since in the time domain you are discrete time, and in the frequency domain you will get a 2π period. Okay, so here is the structure things. And okay, so here is a bit of the spoiler of all the Fourier transform Fourier series we'll talk about. It's a bit confusing to think about it right now, so let's ignore all the duality. But anyway, so the discrete Fourier transform, which is this block here, we are going to derive it like a discrete time. So we are going to do things similar to the continuous time Fourier transform. And so we are going to derive those two equations, and we are going to see a difference where, because your x is discrete time now, and your big, so your small x is discrete time, and that gives a big x 2π period. Okay. And yeah, as we said, there is a duality actually to a Fourier series, but let's ignore that for now. Okay. And yeah. So definitely, so yeah, let's jump straight to a derivation of everything similar things. So it should be easier this time. And as before, we want to derive the Fourier transform from Fourier series. So maybe let's go back to this a little bit. So remember what we do in chapter 4 is we start with the Fourier series equations, and we think those are true, and then we try to, but Fourier series are for periodic function. So we say a periodic function are just periodic function with a really long period. So we start with those, and we try to push the period to infinity, and then we get those. So now we'll do similar thing. We'll start with a discrete time Fourier series and push the n to infinity to try to get the Fourier series, Fourier transform for discrete time function, discrete time periodic function. So yeah, so let's start. So just like before, assume we have this finite duration function or finite support function, and it is discrete time now between some time minus n and minus n1 to n2. And so first we want to make it a periodic function, so we just copy paste it somewhere far away with some big n that's like probably bigger than this n1 plus n2. So we copy paste this infinitely, so now you have so you start with this periodic function x of n, and then you copy paste and you get this x tilde of n, that's a periodic function. Okay. And because x tilde of n is a periodic function, so you can do the Fourier series on it. And so here is the Fourier series formula we had before, and so you will have Fourier series coefficient ak equal to this sum over one period, and your function x tilde of n times this e to the minus jk omega n. Okay. And then just like before, we do the similar operation to change the summation of x tilde back to the summation of xn. So the idea is this is the summation of x tilde over one period times your complex exponential. Oh, sorry. This. Maybe here. Okay. Maybe. Okay, so these two sides are similar, so let's do see this one. Yeah, so you are doing this summation of x tilde times minus complex exponential over one period, but then you notice that summing over, if you are just summing over one period, then x tilde equal to x of n. So instead of summing over x tilde, you can sum x of n here. So you change from x tilde to x of n x. And then you see that since you are summing x, then summing over one period, there is no period, so outside everything is 0. So summing over one period, you can replace with summing everything. So ak, instead of the summing over a tilde over one period, you can just sum over x over minus infinity to plus infinity, just like in a continuous time. Okay. So we arrive at this equation where ak is 1 over n. So from minus infinity to plus infinity, x of n times e to the minus jk omega naught n. Okay. And then just as before, we define this envelope function big X of n, big X of e to the j omega. Well, this is going to be a spectrum, so a bit of spoiler, this is going to be the Fourier transform of our function. But for now, we justify why we want to take this, because we see that the AK here is going to be the samples on this big X. Okay, so see this carefully. So big X is now it's a function of omega, although there is no omega, but we define the function of omega that's e to the summation n, so the same summation n x of n, but we have e to the j omega n here. Okay, so here we have jk omega n, and here we have j omega n. And you see now that AK can be samples on this frequency envelope big X of e to the j omega. So this is a function of omega, but we write it as e to the j omega for reasons we will see later. Okay. But anyway, so what do we mean by AK is sample of this? Because using AK is just, well, there's a 1 over n, so you divide 1 over n, and big X, and you choose your omega as k omega naught. So you see that all the things are just the same, right? So this 1 over n will cover this 1 over n, and you will change omega to k omega naught, where omega naught is just your 2 pi over a period, as always. Yeah. So you see that if you have this envelope function x of big X of e to the j omega, like something like this, then you can read AK for every k, and then right? It's just some point of this big X divided by big N, where your AK is taking this envelope function and value at k omega naught. Okay, and so this big X will cover the information for your AK, and also you can you can calculate your function x tilde from your big X. Okay? So x tilde of n. So now once again use the discrete-time Fourier series formula. So it's the summation aka e to the jk omega naught n over one period. And now we want to write this in terms of this big X. And well, we just have what's AK in terms of big X is 1 over n and big X of e to the jk omega naught big X with omega equal to k omega naught. And we still have this HY e to the jk omega naught n term here. Okay. And then we do something funny. We change our 1 over n. We write it as we write this 1 over n as omega naught over 2 pi. Okay. So now you have 1 over 2 pi just from this changing big 1 over n as 1 over 2 pi, and you have HY omega naught here. And now, just like in the convergence Fourier series, we say that you are summing over something with a very small difference. So just like a continuous time, you will change this summation to an integral, because we say that as n goes to big N goes to infinity, omega naught goes to 0. So you are summing over very small terms. So the terms here are once again like rectangular that's approximating integral. So it's like a rectangular with omega naught, and the height is the value of this curve, that's big X times e to the jk omega naught. So yeah, jk omega naught pi n. Okay. And so as n goes to infinity, you have those sum of triangle with the width of triangle goes smaller and smaller, and we think that just go to the area under this curve. So as n goes to infinity, as big N goes to infinity, this summation becomes an integral with omega, and those points, which were samples of this enveloping function times e to the j omega n, we just think is big X times e to the j omega n. And but we need to be a little careful about the range of summation, right? So the range of summation is the range of summation is always over one period, k from minus n to well, it's one period of n, so depends on how you want to pick. So maybe k from 0 to big N minus 1. And so that range seems to grow as, so the range of k seems to go to infinity as big N goes to infinity. But remember, k times omega naught remained unchanged, right? Or big N times omega naught always remain 2 pi. So this range from k from 0, say k from 0 to big N minus 1. But omega is k times omega naught. So the range of omega always stays something from 0 to 2 pi. Or the minus pi to pi is just some 2 pi range of omega. That's because this big N times omega naught is always 2 pi. And your omega is k times omega naught, so this 0 to n for k means 0 to 2 pi for omega, etc. So this is something different from the continuous time case, where the continuous time case, the integration is from minus infinity to plus infinity. But now we are integrating over a 2 pi range, because this big X is periodic with period 2 pi, so we only integrate in a 2 pi range, although we haven't proved that it's periodic. It's very easy, just like before. And yeah, so that's x tilde. Remember, x tilde is this weird periodic function. But when big N goes to infinity, then we think that O is not very rigorous. We think that all the copy pasting go to infinity, so we just don't see them. And we just think as big N goes to infinity, x tilde equal to xn. And we just say this x tilde we just calculate is the x, and it still has these 2 pi range. And so we have found the 2 equations we want, the Fourier transform pair. So big X, this is the Fourier transform for discrete function. Big X is the summation x e to the minus j omega n. So this equation, and another equation we just find, and small x is 1 over 2 pi. Integrating over 2 pi range, big X e to the j omega n d omega. And so as in chapter 4, this will be the Fourier transform equation, because I told you how you calculate the Fourier transform big X of the small x. And this is the inverse Fourier transform. Or if we want to think this in terms of chapter 3, then this is the synthesis equation for your aperiodic discrete function, although it's a bit hard to imagine now. Now your discrete function is still a linear combination of those e to the j omega n. And yeah, and because you are non-periodic, so your omega can be any continuous time value. Omega can be any continuous time value, but it's still going to be, but the value is only meaningful for things between 0 and 2 pi, because omega and omega plus 2 pi are the same omega. Things e to the j omega and just don't see the extra 2 pi, because you earn only integer values. And anyway, so it's still like a linear combination of this e to the j omega n, although omega is now limited between 0 and 2 pi, or 2 pi period. And no, but it's continuous, so you integrate over all those big X coefficients together, and then you have the extra 2 pi factor, just because that's how we choose our normalization, 1 over 2 pi factor. And on the other way, if you want to know the coefficients associated with some of your function small x, then you do this summation x times e to the minus j omega n. So this is like doing an inner product. So it's sum from minus infinity to plus infinity. Okay. And yeah, so here are some tables or collection of formulas. And once again, these are synthesis equation. Xn 1 over 2 pi integrating over 2 pi period, big X e to the j omega, big X of e to the j omega times e to the j omega and d omega. And analysis relation equation, big X equal to summation x over n e to the minus j omega. And here we have the continuous time Fourier transform to let you compare. You see it's very similar, except you change n to t, and so everything is almost the same when you change n to t. But the biggest change is the integration range is minus infinity to plus infinity here, and it's 2 pi here. And obviously for the analysis relation, you cannot integrate over the discrete function. So instead of integrating over x of t, you have the sum over x of n. And here is the mistake I forgot to correct. Okay, so we have a minus sign here. Okay, so any question for now? So that's the derivation of discrete-time Fourier transform. You see, it's very similar to our derivation on continuous time. I think it is actually a bit easier because there are less infinity here, since one of the integration is only a period of 2 pi. But yeah. So you see, it's very similar to continuous time Fourier transform, but because you have this discrete time here on a time domain, in the frequency domain you will have a period 2 pi, as we always seen for the discrete time function. And now here we explain more notation, and just as before, this integration 2 pi means we are integrating over 2 pi period. It's periodic, so you can pick any interval, but the base ones are either you choose from 0 to 2 pi or you choose minus pi to pi, usually. Because you can see, well, small numbers are easier. Okay. And yeah. So yeah, so say if you integrate from 0, then you have a 0 from 2 pi. Okay. And just like before, the big X, you will have many names, and in particular, we'll call it the spectrum of your small x. Or sometimes I will just say it's the frequency domain signal. Okay. Yeah, so I should probably write that down. Big X, that's the spectrum, and sometimes we say it's a frequency domain signal. Frequency domain signal. And that's because we think we can always transform back and forth between the big X and the small x. And we think they are really holding the same amount of information. So you know big X, you know small x, and you know small x, you know big X. So they hold the same amount of information, you know one, you know the other. So they are like the same thing, you're looking at the two sides. And so sometimes we just say you see small x, you are just looking at the signal in the time domain, and you see big X, you are looking at the signal in the frequency domain. That's the same as what we had in chapter 4. Okay? And okay, a few little things here. And yeah, so here's the derivation. So obviously we derive the discrete Fourier transform as the Fourier series. So Fourier series are for the discrete periodic function, and we just have the Fourier series and make the period infinity. Okay. And so something I keep saying is that now the big X has a period of 2 pi because your small x is discrete time. And the proof is just as before as always. So you think about you change omega to omega plus 2 pi. And you can pretty much use any equation. But here we use the analytic equation, so how you calculate big X from small x. Okay, so you change omega to omega plus 2 pi, and only c dependent omega is this e to the minus j omega in here. And you change omega to omega plus 2 pi, you get h e to the minus 2 pi n. And got a mistake here. So 2 pi n j. Yeah, so you get e to the 2 pi. Or e to the minus j. Wait, let's write j here. 2 pi n j here. And that's e to the 2 pi j to the minus n power, but you know e to the 2 pi j is 1. So this thing just 1. Okay. And that doesn't change anything, and so you change omega to omega plus 2 pi, you just get back to the same big X. Okay. So I prove that big X is periodic with period 2 pi. And that's true for any discrete case. So remember, this was also true in the discrete Fourier series. And that is also why we are using this very annoying notation. So notice that in the chapter 4, we are calling this big X x of j omega. And here we are using big X of e to the j omega, because that will cover the fact that your omega has a 2 pi period. So you think about this e to the j omega as an actual number, then e to the j omega will equal to, I should have parentheses here, sorry. So this big X of j omega will, what happened? Equal to big X of, is e to the j omega equal to e to the j omega times 2 pi, right? Just like just because e to the 2 pi j equals to 1 as before. So this is a clear way to get rid of all the redundancy on omega, because omega I and omega alpha 2 pi is the same omega basically for discrete time. Yeah, but really it's just some notation trick here. Actually makes the writing things a little annoying because they are mostly to type. But anyway, you can kind of think this just as a function of omega, and we'll plot it as a function of omega. But we would like to write it as function of e to a j omega to remind us that omega has this period 2 pi. Okay. Any question? If not, let's see some examples. So first we have an example that we didn't show calculation, but just as a reminder to you that this is a thing we have seen in the periodic case also. So the low frequency things are now the omega has a period 2 pi, and the low frequency things are things around omega equals 0 or omega equals 2 pi. Okay. So if we have a function that looks like this, then we will have it's kind of low frequency, and our frequency domain signal will concentrate around this 0 and 2 pi and things. And the high frequency thing, now high frequency signal means that it keeps going up, down, up, down, up, down, up, down, because you have a discrete time, so that's the highest frequency you can get. For every n you go up, down, up, down, up, down. And in the time domain, these up, down things means that your signal is concentrated, or your spectrum is concentrated around this odd integer of pi. So pi minus pi and 3 pi minus 3 pi, etc. Okay, so this is similar to so this is similar to with the discrete-time Fourier series, except that now your x is not periodic, so it can go anywhere from -infinity to +infinity, and your big X is still periodic, but now it's continuous. Right. So before we had small, so for in the discrete-time Fourier series, this is discrete and this is discrete. It's very symmetric. But now this is discrete and this is still continuous, but it has a period 2 pi. Okay. Okay, so that's qualitative talk. Let's see actual example with calculation. So kind of our favorite function is this Chaplov exponential decay. So we did have a picture for it now, but it's u of n, so Chaplov is n equals 0 and a to n, and we want things to converge, so we have the absolute value of a is less than 1. Okay? So it's an exponential decay, but it's actually a complex number, so it's a bit weird. But anyway, it's a complex number, we can still plug in our formula. So we plug our big X formula is summation is big A, summation of your small x and your e to a minus j omega n. And this is kind of our favorite because the calculation is easy. It's power series. This is a thing that we kind of know how to sum the best. So you have a to n and this e to a minus j omega to n, so it's just a times e to a minus j omega to n, and this u will chop off your n at 0. So you have 0 to infinity is power series, and because your a absolute value is less than 1, so this is converge, and you can just use this 1 over 1 minus r notation equation. Okay. And yeah, so that's easy. It's power series. You use a power series formula, you get this result. And now you plot this, it's a bit weird. So you want to plot this, it depends on a. And for now, we give two plot where we assume a is real. So so a is real, and if a is bigger than 0, then the amplitude look at this and the angle look at this. So amplitude are a little easier to see. Okay. So we need to think about this in complex plane, right? Because now this is a complex value. So what's what's a to the e minus j omega? So you think about this value. So this is a times e to the minus j omega in complex plane. So it's they are real and imaginary. And well, if a is real and bigger than 1, so when omega is to 0, then you have a is something in a real line, right? And then you start multiplying it with e to the minus j omega, and that's adding a complex phase. So you are basically working on this circle where the radius is absolute value of a, and so you minus j omega, so as omega from 0 to 2 pi, you work on this circle from 0 to pi. So the angle you work is 0 to 2 pi. Okay, so that's this a equal minus j omega term, but what's our big X actually? So we have 1 minus this term, right? So 1 is here. So you are so this value is 1 over the distance between 1 and your point, right? So you see that when your omega to 0, your e to the a times e to the minus j omega is closest to 1. And because you are doing 1 over, then the amplitude is highest. And then you have omega equal to pi, then you are working the furthest away from your 1. So you are at the lowest point. And then you walk back, then when omega to 2 pi, you walk back, and you are back to the highest point. But what happens if you have a is less than 0? A is less than 0, then your a times e to the minus j omega start from here, right? Because a is some negative real number. And so you start of the furthest away from your 1, and as omega from 0 to pi, so the lowest point is omega equals 0, and omega goes to pi, then you walk to this point, then you are closest to your 1, so this 1 over your 1 minus this thing is the highest, and then you walk back, so omega from pi to 2 pi, and and you walk back as omega from pi to 2 pi, and this value decreases back. Okay. Question about this frequency domain analysis, and obviously you have a different angle. Angle will go. There are also phase, and the phase will go up and down, and you can check it out. It's actually correct. And more interpretation. So does this actually make sense? So we want to see. So you see that we said that if you think around 0, then it's low frequency. You pick around pi is high frequency, right? So why is this true? That's because you think about this thing. If you have real A, then it's just a decay, and it's kind of low frequency. But it's easier to see why this is a high frequency, because you think if A is a negative real number, then this A to N is going to go up, down, and up, down, up, down, up, down, right? Because A has a minus sign in it. And so this will kind of go like this, although it's actually an exponential decay. But it has this up, down, and up, down, up, down structure because you have a minus 1 in your A, and that will correspond to high frequency. And so that checks with our calculation here. Okay? Any question? You go and buy this. Okay, and so if we buy this, then let's see another example. So this example will show a picture on the next page. And anyway, so now we have this two-sided decay, also seeing this kind of thing. So we have A to the absolute value of n, and it will look like this. Say if you have A that's positive. Okay? And but here we just say the absolute value of A is less than 1, so this thing kind of is converges and go to infinity. Okay, so it's like this two-sided decay. we've seen similar thing in continuous time, but no, it's discrete time, obviously. And we can also brute force calculate our big X. And so if this on n minus infinity plus infinity, your x times e to the minus j omega n. And it's really not too different. You just see that, well, you have an exponential decay on the positive n and exponential decay on the negative n. So you just break them into this positive n part and negative n part. And both exponential decay, and so you will get a 2-power series on them. And you need to be a little careful about your breaking because you only have one n equal to 0, so you need to pick n equal to 0 on one side here. You put n equal to 0 to the plus side, and so this side you have n start from -1. And anyway, you have those 2-power series. And if you do your negative sign and first turn things carefully, hopefully we do everything correct, you get a 2-power series, and infinite power series, you plug in the formula and get those two answers, and you get your big X. And so yeah. And now your big X is actually real now. For real A. And that kind of was just like before, right? Although we haven't talked about property, but just like before, this x of n is even and real. And so you can expect that your big X will also be even and real. Okay, for real A. And okay, so here is your even and real big X. And so you see that for this positive A, then your X is quite smooth two-sided exponential decay, and your big X once again concentrated around low frequency. And okay, so low frequency is kind of hard to see just from here, but from the calculation. So the calculation here, and you can calculate from here, plot it, and see that it concentrated from low frequency. And but the important thing to see here is that once again it's periodic with period 2π. Because so let's look at this a little more careful. So this thing it only depends on omega on this minus 2a times cosine omega term, right? And since it only depends on omega is cosine omega, and the cosine omega has a period 2π, obviously this thing is period 2π. And if you think this a bit more carefully, you will see it has a peak around 0, because if the lower part is smaller, then the whole thing is larger, right? And it's smaller when this cosine omega is larger, and it's largest around omega 0, 2π, etc. Right? Because you are minus 2a, which is negative, times this cosine omega, so you want cosine omega to be large. Then you are subtracting more things, and this whole thing, subtracting more things on the lower part, so the whole thing will be bigger, etc. Okay, so here is an example, and we have another example. So kind of our favorite square wave function, right? And so in chapter 4 we spent quite a few time looking at them. So the time domain we have a square wave. Then in chapter 4 we have the frequency domain. You have the sinc function, which is sine omega something over omega something. But here is discrete time, so we no longer get a sinc function. Now we get this sine over sine, which we also kind of see in chapter 3 when we talk about discrete time. And we want sine over sine because we want a periodic function with period 2π. And you can check it out, this sine over sine. So we have a sine with higher frequency actually omega 1. Omega times n1, where n1 n1 is the width here, and then over another sine. Yeah, it's a bit weird, but anyway, another sine over omega 2, and these were periodic with period 2 pi. Okay. Although, yeah. Well, there is 1/2 here, but it's also actually period with period 2 pi. It actually has period 2 pi. Yeah. And anyway, here's the plot with ny equal to 2, so you have 2 peak per 2 pi. And you can measure if ny is larger, you have more smaller peak here. Okay. So those are the examples. Now we have 10 minutes. Okay, so we can probably finish this. And now we derive those formulas. And now we have convergence issue. So this is a bit tricky. Remember when we have discrete-time Fourier series, we say there is no convergence issue. But here we have a kind of weird convergence issue. And anyway, we derive those two equations. Your Fourier transform pair assume our x of n has finite support. And but actually for infinite support x of n, so maybe so things like this, you have infinite support right equals to minus infinity plus infinity. Your Fourier transform pair still holds in some sense. Yeah, but not every function is hold. Say for example, you can imagine if instead of exponential decay you have like growing exponential, then your integration will just not converge, right? So the summation will just not converge if your x of n just goes to infinity, then go to infinity. Okay, so we need to careful about the convergence. And here we are staying extra lazy. Okay, and yeah, basically we just say those are the two equations that two conditions that guarantees that your things converge. So either your signal is absolutely summable in the time domain, or it has finite energy in the time domain. Okay. And yeah, so if you have those kind of things, you can kind of see that this 5.9 should converge, right? Because you are summing over finite things. So then your big X will converge, and that will be nice. And now we kind of gloss over this, but for 5.8, you have this integration. And yeah, we just say it's over a finite interval, so if your big X is not too bad, it should converge. Okay, and yeah, I think this is a bit tricky because if you want to be careful about convergence here, you will jump to the star, right? Wait, maybe I can go to. So hopefully this is not too. Let's see, can I go to maybe 1? Okay, yeah. So remember we have this duality. I said we can kind of forget. So the thing we do here is actually kind of due to the continuous-time Fourier series, because you see one of them is discrete and one of them is periodic, and then continuous-time series we also have one of them is periodic and one of them is discrete. And in the continuous-time Fourier series, we actually see that the convergence is kind of funny, because you want like the directional conditions on our time domain. And so if your time domain is continuous periodic function is very bad, then say you have like infinite number of up and down, or it's a square function, then when you try to add this back, then you will have some trouble. And so the textbook don't quite say, but you can imagine that. So this continuous time periodic function will correspond to this continuous frequency periodic function, right? And so we can imagine that if this frequency function is really bad, say it doesn't satisfy the ratio conditions, and then you will have trouble converge back when you sum it back. But I think here the point is, even though we say the frequency domain and the time domain are like equivalent to each other, they are duality and they are symmetric to each other, we still care about the time domain function a little bit more. So we kind of think the time domain function is the actual physical function we are caring about, and so we are writing our convergence relationship in terms of our time domain function. And so that's why we have, okay, about right, yeah. And that's why we have our convergence condition here in terms of those absolutely summable in terms of small x and finite entry instead of small x. And yeah. And we just didn't say, and we just kind of assume our big X is kind of nice, and so when you integrate it, it's over finite interval, and the integration will usually converge. Okay. And also we want to say that we focus on time domain, then we'll see that the time domain you actually get no Gibbs phenomena. So meaning that, so for example, for this, so you have a square wave function in time domain, even though you have this sharp change, but it's discrete time, so kind of not that sharp because it's discrete anyway. And so we'll see that this kind of square wave function, when you go to big X and integrate it back, then there is no Gibbs phenomena you can integrate back to the same thing. And we can kind of see in this example where okay, so this is also like a square wave function, although it's a very thin with square, where say our function is just delta of n, so it's just one spike at n equal to 0. Then you can apply your formula and you see your big X is the constant function. Well, it's also periodic with period 2 pi, right? And then we think about you transform this back to your X of n. And obviously you can apply the transform. But so kind of like in chapter 3 we check the Gibbs phenomena we want to see. So here we say if you just apply formula you want to integrate some 2 pi interval, so mainly from minus omega from minus pi to pi. And think about we change the integration interval from some minus omega to omega, and you increase the omega slowly to like minus pi to pi. And let's see what happens. So if you apply the formula here, so this integration from minus, not omega, so minus w to w, and you do the integration, it's not too hard, you see it's sine wn over pi n. And so you see there is no Gibbs phenomena as your w goes to pi, because this is what happens. So here we just have a result plot here. So w equal to pi over 4, you have this kind of thing. And so different w increasing from pi over 4 and 3 pi over 8, etc. And you increase to pi. So you can see that things kind of, as your integration range increase, so you kind of like Gibbs phenomena where you get the oscillation faster and faster. But kind of because you are only sampling things on integer value, right? So if your oscillation gets too fast, then you just don't see it. And so you see that when your w goes to pi, then this integration converges back to your single delta function here perfectly. So you see that you get the discrete jump in your time domain, and you actually get no Gibbs phenomena when you integration back. And but you can kind of guess from duality that if you're time domain you don't care about this, but your frequency domain you have a block, then you probably get some Gibbs phenomena when you integrate from your sinc function on your time domain, etc. Okay, so we are a little over time. And any question? Otherwise, we'll talk more about discrete Fourier transform next time on Friday. Okay? Yeah. So see you next time.